Hello guys, today in this video we are discussing about graded impurity distribution, and because of this graded impurity distribution, what will be the induced electric field? Okay, so now let us first try to understand what is graded impurity distribution or non-uniform doping, all right? So graded impurity distribution, it says that the semiconductor is non-uniformly doped with impurity atoms, right? So let us consider here a semiconductor that is non-uniformly doped with donor impurity atoms, right? So if the semiconductor is in thermal equilibrium, okay, so it is doped non-uniformly, but it is in thermal equilibrium. There is no external electric field given to the semiconductor. So in this case, when the semiconductor is in thermal equilibrium, the Fermi energy level we know will be constant throughout the crystal, right? So now how I will show you the energy band diagram for a non-uniformly doped donor impurity atoms, right, which is in thermal equilibrium, right? This first thing we said that the Fermi energy level will be constant throughout because it is in thermal equilibrium. No external excitation is given. So let us draw the Fermi energy level first, right? Then we said it is, the impurity is distributed non-uniformly, right? Doped non-uniformly. That's why the term graded is used, right? So if I will draw, uh, the conduction band this way, okay, suppose this is my conduction band. Here you can clearly see that the gap between the conduction band and the conduction band here, conduction energy EC that we said, and the Fermi energy. So the gap you can see continuously decreasing as you will move from uh, right to left, actually towards left. You can see, right, the distance between EC and EF decreases. That clearly indicates towards this, towards left, you will see the gap between EC and EF decreases. What do you mean by this? EC minus EF actually decreases. And when this will happen, EC minus EF will decrease when the impurity concentration is more. Impurity concentration more means what? Ideally the Fermi energy level will be closer to the conduction band, right? So here if you will see, as you go towards left, you can see as the distance between EC and EF decreases, so the concentration of actually electrons or concentration of the impurity atoms will increase, right? So this can be done, this can be drawn to indicate that it is graded impurity distribution, right? So let us now draw all other bands, like suppose here I will say EC. Exactly in between I can draw the same way, which will be parallel to our EC, okay, will be the intrinsic Fermi energy level Fi. This is our intrinsic Fermi energy level, which is somewhere, I mean, in between EC and EV, and then this is your EV. So you need to keep in mind why this particular band diagram is drawn this way, just to ensure that the gap between EC and EV is constant throughout. You can see EC, EV, and EFI, all three, they are parallel to each other. But we said that the Fermi energy level is constant throughout. Okay, so considering the Fermi energy level to be the reference, right? So here Fermi energy level is considered to be the reference and is having a constant value. So if this indicates the energy value, okay, this indicates the energy axis here. You can see that the Fermi energy level is at a constant value over here. The conduction band accordingly, okay, varies with respect to the Fermi energy level. The intrinsic Fermi energy level also varies with respect to the Fermi energy level, and the valence band also varies with respect to the Fermi energy level. Here Fermi energy level is considered to be the reference and is considered to be constant in thermal equilibrium as long as there is no excitation, external excitation is given to the semiconductor. So I think you can understand this way. So here this is your energy axis, and suppose this is our distance, right? So in one dimension we are considering. So it clearly shows you that the doping concentration, if you will move in the positive x direction, the doping concentration gradually decreases, right? So the doping concentration gradually decreases, right, as your x value increases, right, as you are moving away from this end to this end, right, or you said left to right, your doping concentration increases. In other words, I said if you're moving from right to left, then your doping concentration increases. So this is a schematic diagram just to indicate graded impurity distribution. Now in this case, when the semiconductor is doped non-uniformly, then what will happen to the electric field? That is what we are going to find out, right? So here you can see, as we said, there is a difference in the concentration, or there is a concentration gradient or density gradient as you move along the x direction. So there will be diffusion of majority carrier electrons from the region of high concentration. So if you will see, this region is the high concentration and this is the low concentration of the electrons. So the electrons will start moving from high concentration to low concentration, as we know, using your diffusion mechanism. So in this direction it will move, right? So when these electrons, suppose I will just show you schematically, you need to just imagine that way. Okay, so suppose we have electrons concentrated at one end here. Okay, let me just take electrons over here, right? There are electrons here, and when these electrons will move, okay, to the lower concentration region, then what it will leave here? It will leave a positively charged donor ion, because that is what we said, because you have doped it non-uniformly. So what will happen here, when this electron will move, okay, towards the low concentration region, then what you will see over here is a positive ion, right? Positively charged donor ion, right? So what will happen here, you got the electron that will be here. Similarly, this electron will also move, and you got the electron over here, and this will be the positive ion now. Okay, positive ion. So this way what will happen, separation of, you can see these negative charged electrons and these positively charged donor ions. Okay, you will see. So this will induced electric field. So an electric field will be induced now. Electric field will be induced. So we need to find out what is the value of the induced electric field over here. Okay. So here, if you want to know this, I mean, why this EC and EF are close for a for a heavily doped donor impurity atom, there is a formula we have already derived in one of the videos you can refer. Okay, which is EC minus EF is equal to KT by E logarithm of NC, effective density of states in the conduction band, divided by ND. This is for donor impurity atom. Okay, ND is the donor impurity atom concentration that you have had. So as ND value increases here, you can see EC minus EF will be less. So this way you can understand why this graded impurity distribution. There is a the conduction band is relatively close to the Fermi energy level when there is highly doped region, right? Heavily doped region. Okay, so now what we said, the separation of these positive and negative charges, right? This will induce an electric field that is in a direction to oppose the diffusion process. Now what will happen? More number of electrons are moving from high concentration to lower concentration. As a result, you got the charge separation. There will be a time when there will be more accumulation of negative charges at this region, okay, in this region. So further flow of electrons from this region, further flow of electrons from this region will now be prevented by this induced electric field, right? So this will I mean, the induced electric field will prevent the further flow of electrons, right? Now let us find it out mathematically. What is the induced electric field here? Okay, how to determine the value? This is what we are going to do, right? So now you got the value, the difference between EC and EF, and at the same time you can also see the difference between here the EF and EFI values. Okay, you can see the difference between EF and EFI value, right? So if you want to write the electric potential, okay, um, the electric potential, okay, in, I mean, from energy, if you want to find out, right, what is the change in the Fermi energy level. Initially it was EFI when it was intrinsic Fermi energy level, like intrinsic semiconductor. Then you doped it, and because of doping the form, there is a change in the Fermi energy level. So you initially you have a value EFI, then for this much doping you got EF, then you got this. As the doping profile increases, your change in the Fermi energy level occurs, right? So now if I will write what is the potential, corresponding potential for this change, what we can write is phi is the potential I'm writing, can be written as what is the change in the shift of the Fermi energy level with respect to the intrinsic Fermi energy level divided by E. This is simple. W is equal to QV, we know, right? So you just divided the electronic charge. Now the electric field, if you write from this, okay, in one dimension, because we consider one dimensional electric field here. So if I'll write the electric field in one dimension, I'm just putting Ex, the variation of electric field, or the electric field as a function of X, right? We can write this to be minus d phi by dx. This is known, we have already done this. E is equal to minus d phi by dx. So let us now take the derivative. So we have minus d by dx of this phi, I will substitute. Okay, so phi value we wrote as ef minus efi divided by E. Okay, now as we said, thermal equilibrium, for thermal equilibrium we considered that the energy is constant. If you see here, the energy value, this value corresponds to constant value of Fermi energy, right, in thermal equilibrium. So the EF is considered to be constant, right? So EF is considered to be constant here. What is varying with respect to X, if you will see, this is EFI, you can see EFI is actually varying with respect to X, you can see. Okay, with respect to X, the EFI value is varying. So that will exist if I'll take the differentiation. So what we can write now, you got minus d by dx of EF. E, this small e is constant, you take it outside, no problem. So this will be 0 because it's constant, and then we will remain with minus d by dx of this EFI by small e. So that we will write minus minus plus. So we got 1 by E is constant, and then we got d EFI by dx. Okay, so your electric field as a function of X, if you want to write, you need to find out the differentiation, how the Fermi energy level, intrinsic Fermi energy level actually varies with respect to X. This is what we are going to find out. Okay, so this is this DEFI by dx actually we need to find out, so that I can substitute, or from some equation I will find out this DEFI by dx, and will substitute here to know the value of induced electric field in a non-uniformly doped semiconductor, or because of graded impurity distribution in semiconductor, right? So if you remember one equation that we have done earlier, that is N0, the concentration of electrons, right, in the conduction band, we have derived one expression in terms of intrinsic carrier concentration given by Ni e to the power exponential to the power. This is EF minus EFI. This is what we need, EF minus EFI, the shift in the Fermi energy level, and then K Boltzmann constant, and T is the temperature, absolute temperature, right? Now this N0 is actually what, if you are considering the doping concentration, okay, to be Nd, and complete ionization, that means all the dopant atoms have contributed one donor electron. So this Nd will be like complete Nd, number of electrons donated by each donor atom, plus Ni, intrinsic carrier concentration. But if we will consider this Ni to be very, very less, this value is very, very less as compared to this Nd, okay, and we said it is graded impurity distribution. So this Nd further can be written as, Nd is a function of X. So here we ignored this Ni value, saying that this value of Ni is very less as compared to the doped concentration, which is a function of, which is varying with respect to X, because we said graded impurity distribution. So this N0 nearly equal to Nd I will consider, because I want to write in the form of Nd, graded impurity distribution. That's the reason we wrote N0 is nearly equal to Nd, capital Nd as a function of X, ignoring this Ni value. And so this is why I told you that you need to consider complete ionization, and the donor impurity concentration should be much larger than the intrinsic carrier concentration. Then we can consider this practically. Okay, so what will be the next step? We can write, so Ni exponential of this bracketed term Ef minus EFI divided by Kt, okay, can be written as ndx. This ndx is your graded impurity distribution, right? So now simple mathematical steps, we can rewrite it, the above equation as Ef minus EFI can be written as, here you can see e to the power this, so can be written as Kt times logarithm of this ndx divided by this Ni, right? We can write this way. Okay, so once you get this value Ef minus EFI, what we need is, we need the DEFI by dx. Okay, how the intrinsic Fermi energy level changes with respect to X, and we got this EFI. Ef is constant, so no problem. If I'll take the derivative, it will be 0, so I can write DEFI by dx as a function of ndx now, right? So if I will write that, so if I'll take the derivative with respect to X for both the sides, okay, Ef minus EFI, okay, can now be written as Kt, and the derivative of logarithm of this term, okay, which can be written as Kt by, this is ndx, and d ndx by dx. Okay, so you got this, actually 1 by Ni, here you can see this Ni is already there, so 1 by this whole thing will give you this Ni in the numerator, and again that there will be 1 by Ni, so Ni cancels, so you got this. Okay, so here d by dx of Ef, the first term will vanish, the second term will exist, and from that we can find out what is dEFI by dx. So if we will rewrite the equation, then you can just see back, so this term will vanish if I'll take the derivative d by dx of this, the second term will exist, and so I can write minus defi over dx is equal to Kt by Nd x, the graded impurity distribution, and then dnd x by dx. Okay, this gives you the variation of the impurity distribution with respect to X, right? Let us now substitute in our electric field, induced electric field, because of the charge separation, okay, because of the mechanism of diffusion, right? There was a difference in concentration gradient, so we said that the charge electrons, here majority charge electrons are moving to the other direction, low concentration. As a result, this charge separation occurred, right? So we need to substitute in that. So electric field we got was minus Kt, uh, sorry, we just derived it as minus, 1 by E, and it was, once again, 1 by E and DEFI by dx. Substitute that, DEFI by dx, and now you substitute this DEFI by dx as minus Kt by ndx, the rest. So what we can write, minus Kt by E, and then that 1 by Ndx, okay, and then you got dNd by dx. Okay, so this is our one-dimensional electric field. Considering that the the doping is non-uniform, okay, and there is a concentration gradient, density gradient in the semiconductor. So if this is the case, then this amount of electric field will be induced, and this electric field, induced electric field, depends upon what? This minus kT by E, which is considered to be constant at a certain temperature. K is constant, E is constant. 1 by ndx, this is the variable here. Ndx is what? The doping concentration as a function of x you wrote, and then dnd by dx, that gives you the first order derivative of this ndx, how actually the doping concentration varies with respect to x. So this whole thing will give us the induced electric field in one dimension, right? Now, as we are discussing the thermal equilibrium condition. So thermal equilibrium condition, we said, in thermal equilibrium, when there is no external excitation, just there is a semiconductor here, and this semiconductor is non-uniformly doped, right? Non-uniformly doped. Now, if it is a non-uniformly doped semiconductor where there is no external excitation given, no external voltage given, no external applied electric field given, then there must be no current here. Okay, no current, whatever the mechanism. We know that here, if you will give, like, we said we got the induced electric field. So if there is an induced electric field, then the charge carriers will start moving because of this induced electric field, which will give rise to what? Drift, carrier drift. So carrier drift, we know, if you write the carrier drift of electrons, for example, we can write the carrier drift of electrons. Okay, a drift of electrons, if I'll write n drf, drf for drift, n for electron, then we got E n mu n ex, right? Similarly for hole, if I'll write, it should give us jp drf drift, that must be E concentration of P, mu P mobility of hole, and then the induced electric field. So if there is a non-zero induced electric field over here, then there must be some drift of electron and drift of hole. As a result, there must be some drift current density as well. So drift current density because of electrons and holes, right? Similarly, because there is some concentration gradient difference in concentration, there will be diffusion as well, right? So for example, for electron diffusion, we said Jn diffusion, if I'll write the value we just discussed, E dn, and this dn by dx, this will also be there, right? And then similarly for hole, if you write jp, this is dif. For diffusion, I'm writing there is a minus sign, E dp, and dp by dx over here, right? So dp by dx over here. Okay, so now what we got, if I'll write the total current density, the total current density must be zero. We said the total current density will be zero because there is no external excitation given, so no current ideally. If you will see the semiconductor, non-uniformly doped semiconductor, there is an induced electric field which will lead to diffusion, which will lead to drift current. There is a concentration gradient which will lead to diffusion current. But the sum total of all these terminologies, like all these four terms that we got in the in the what in the total current density must be zero, right? So individually, if you write, okay, so individually, if I write, the current density due to electrons must be zero, the current density due to holes must also be zero. So if I write for a thermal equilibrium semiconductor which is non-uniformly doped, where we got an induced electric field, and also there will be diffusion of electrons, okay, drift of electrons, and diffusion of electrons, but it is in thermal equilibrium, so there will be no current. Okay, so what would we can write then, the current density due to electrons must be zero, which now can be equated to E n mu n, that is the drift current because of electron, and the diffusion current similarly E dn and dn by dx. Again, here I will write n here is nothing but your nd, which is graded impurity, suppose ndx. So I will substitute this, okay, so that I can write jn is equal to 0, which can be written as E, and the doping concentration here NdX, and mu n, of course mu n will be there, plus E dn, and then this d n d x by dx. Okay, this we can write. Okay, now substitute the value of E. Sorry, I missed one thing here, the applied electric field. Of course, there is applied electric field Ex. Okay, and then you substitute the value of Ex that we determined. Okay, the Ex value here, minus kt by E 1 by ndx dnd by dx in this equation. Okay, so if I'll substitute the Ex value here, what I will obtain that this 0 must be equal to minus E, substituting the value of this Ex, mu n n dx kt by E 1 by n dx function of x, and then dn d by dx of n dx, right, plus the second term here E dn d by dx, right. So you can see these two terms actually is equal to 0, so each term must be equal, they must be equal, right. So we can just equate these two terminologies, so you can see whatever will be cancelled, you cancel those. I can see e got cancelled, ndx and ndx got cancelled. So what else? Yeah, that is it, right. So we can now rewrite whatever is remaining. Yeah, so yeah, let me just see this mu n and kt and dnd by dx here. Okay, and then we got any other thing that can be cancelled. Let me just equate it, then I will it will be better, we can see. Okay, because dnd by dx will also be cancelled, so I can just rewrite it. So let me just rewrite it, then I will cancel E dnd x by dx must be equal to E mu n n dx divided by n dx, and then there was a term kt by E, and dnd multiplied with dnd by dx. Okay, so this is the term, let me just cancel, let me just equate it and then cancel. So E dnd by dx must be equal to this, taking this to the other side, and then you can see and cancel whatever you can see here. Ndx got cancelled, E got cancelled. Okay, and dnd by dx from both the sides you can see. Then we got this dn over here, diffusion coefficient for electron, and this mu n here. So dn divided by mu n, the mobility, diffusion coefficient of electron and mobility of electron must be is equal to, you got this kt over here and this E over here, so kt by E, right. So you can now see that there is a relationship between the diffusion coefficient for electron and the mobility of electron. They are not actually independent of each other. So at any temperature, if the semiconductor is non-uniformly doped, or there is a graded impurity distribution, right, there will be diffusion and mobility in both the both the mechanisms will occur in such a way that the current density will be zero, because there is no external excitation given to the semiconductor. So the current density, electron current density and the whole current density, because of drift and diffusion, both will be zero, right. So considering that, we understood that there is a relationship between the diffusion coefficient and the mobility. So these are not actually independent parameters. The diffusion coefficient and the mobility, they are not independent parameters. They are related to each other, right? The same way you can write for whole. Okay, for whole we can also write for whole. If you will write for holes, if you will write Then you can write dp, the diffusion coefficient for holes, divided by mu p, the mobility of holes, can be written as kt by e, right? This, okay, this particular relationship between the mobility and the diffusion coefficient is known as Einstein relation. Einstein relation. Okay, so what is Einstein relation? This particular relation actually connects, or relates the diffusion coefficient of a charge carrier to its mobility, right? What are the, I mean, it is a constant. You can see k is your Boltzmann constant, T is the temperature, E is the electronic charge, right? So here in this video, what we considered the graded impurity distribution. When the semiconductor is non-uniformly doped, what will be the induced electric field, and considering that value of induced electric field and finding the variation of this intrinsic Fermi energy level with respect to x and substituting it, we got a relationship between the diffusion coefficient and the mobility in thermal equilibrium, right? So thermal equilibrium, as there is no current because of electron or because of holes, we use that concept and we obtain the relationship between the diffusion coefficient and mobility. Okay, thank you for watching. This is it in this video. We will come with a new topic in the next video.